Hey, good afternoon to everyone on Zoom. If you can just give me a mic thumbs up, you can hear me well. It'd be highly appreciated. Test, test. Hello. Thank you, Tyler. Switch this to. I think they organize this. Okay, we're at the 4:30 mark. We can go ahead and begin. So as usual, we'll just talk a few course logistics, then we will dive to our lecture, primarily chapter 3. And so the first things first is regarding the assignment, programming assignment 1 has been released. So just wanted to announce you to that. I made an announcement. I just figured I'd say it also on the lecture to make sure that you are aware of the. This is better. You are aware that the assignment has been published. So it is due on the 5th of October. So you should have some time, and it's relatively closer to what we discussed in class. If we have some time after the lecture today, we will talk about it a little bit in detail. But currently we are in, this one has not been published, so this has to be published for you guys. Hey, Howard. So currently we're starting a new chapter, which is chapter 3. We wrapped up chapter 2 in the last lecture. So here's where we're gonna start. And then towards the end of the lecture, we'll we'll talk about the programming assignment a little bit more, and then we will discuss some questions regarding question 1 that were raised. Okay, so what we can do is now we can start the lecture. Before we start, does anyone have any questions, concerns, anything like that? No? Okay, that's good. Okay. So I know last lecture on Monday, we talked about the last aspect of chapter 2, which is the programming assignment, specifically the socket programming assignment. And we discussed TCP and UDP, the 2 main protocols that are used when it comes to the transferring of packets or data through the network infrastructure itself. So today we are moving a layer down, in terms of networking related. So this is going to be the transport layer. So it's one of them important key pieces that we will talk about, and we want to see how the communication takes place in the internet. We have looked at the application and we know how the application works and the different protocols, but the transport layer, we want to see how do computers reliably talk to each other and how do they communicate with each other, whether the packets don't get lost or corrupted. So we'll study important things like how identities are managed, how to keep both sides in sync, how to avoid overwhelming the network, and most importantly, every time we move down a chapter, we're gonna reference the other chapter. It doesn't mean that we are not gonna reference the application layer. We will, And we will talk about the two main things within the transport layer, which is the UDP and TCP. So let's go ahead and begin. So for the objectives of this lecture is to understand the role of the transport layer in delivering data to the correct process. We also want to learn how multiplexing works at the sender, where you have a combination of data that is combined from multiple users and being sent down to the server. Demultiplexing works at the receiver. Once the receiver receives that data and knows how to separate it, how to separate the data based on the IP addresses and port numbers. We will primarily talk about the both of the protocols today when it comes to demultiplexing. So UDP is, we know it's based on a destination port number, and TCP is based on a 4-tuple that we will discuss today with examples. Because we know UDP does not have, it's connectionless, so it does not have anything that is a handshake similar to TCP. And then we want to apply these principles to real-world client-server scenarios like web, streaming, and voice apps. So as usual, the acknowledgement, the lecture is being recorded, and ample of the slides are derived from here, from the book. So the overview of the transport layer is we want to understand the transport layer itself and what it does. So the principles that we'll look at is multiplexing and demultiplexing, which decides which application and it could be an email or web each packet belongs to. We'll talk about reliable data transfer, making sure that data isn't lost or corrupted. And that is primarily with TCP. We'll talk about flow control. How do we keep a fast sender? How do we keep the network from being overwhelmed? And at the same time, it is not being delivered in a slow fashion. We'll also talk about congestion control, which preventing too much traffic that would happen on the network, where we might have multiple clients that are using the application and using several processes on the application. Second, we'll look at the protocols, and these protocols you should already have an idea or a foundation, whether it's theoretical or a little bit of hands-on, on how they work exactly. We know that UDP is more simple, no connection, just sends the packets with the best effort, and it's faster, but not reliable. And then TCP is more connection-oriented, transport, reliable, flow congestion, and control. So by the end of this lecture, you should know the theory principles and the practice of UDP and TCP. So here's the roadmap. The roadmap and the plan for this chapter is that, and here's what we're going to cover. We're going to cover the transport layer as a service itself and what it does as an overview of the layer. And then we'll go step by step. We'll talk about multiplexing and demultiplexing. We'll talk about UDP, reliable data transfer protocols. We'll talk about TCP. We'll also talk about congestion control. And then we'll talk about evolution of the transport layer, how it has been grown over time from how it started to now. So this is just the table of content that we are going through. You might notice that on the figure here, we have, we know the OSI model consists of 7 layers, but we are directly going from the application to the transport layer, as this one deals mostly with the network infrastructure. You can think of the other 2 layers, like the session and presentation layer, are dealing mostly with the application. It does not mean they're not necessary in a bigger umbrella, but when it comes to networking, mostly these are the 5 layers that we will focus on more primarily. So we see this figure, and we have seen it multiple times, and we have national or global internet service providers, we have local or regional, we have content provider networks. We talked about Netflix or YouTube that provides these servers for their users for content distribution. We have enterprise networks, we have home networks, we have mobile networks. So what does the transport layer do? The transport layer, its job is that it will provide logical communication between applications, processes that are running on different devices. So we might have a device from the mobile network that is being connected to a server. We could have another device from the home network that is being connected to the server. So That's what the transport layer primarily does. So it will do a logical end-to-end transport. So even though that we have two apps that are running on different hosts at different complex systems, it feels like they are directly connected to each other. So no matter what the application is or the device, the transport layer is going to be the one that is responsible for that. So here, when we see the arrow up top that says logical end-to-end, what that means is that even though the packets actually travel hop by hop through routers and networks, from the application point of view, it looks like a straight line between the two application or the two hosts. So that is the idea with the transport layer. How does it work in practice? We know the foundational idea of the transport layer now. We want to understand how it works. So when we want to understand how it works, we talk about two things. We talk about the sender and the receiver, or the client and the server. So on the sender side, what happens is that we are using the application. It takes the large application messages, and then it breaks it down to smaller segments, also mentioned as fragmentation or encapsulation. On the receiver side, what it does it collects those segments and reassembles them back to the original message, then delivers them back to the application. So this ensures that the application layer itself or the applications do not worry about the packet sizes. This is something that is controlled by the transport layer as a service. And then how do we transfer, or how do the sender and receiver communicate with each other, or that data is getting flown between them? Is we use TCP and UDP. These are the internet protocols that are available for these internet applications. So almost all the internet applications uses one of these two applications, depending on the primary reason for it. If it's video, usually it uses more of UDP. So to understand the analogy, here's an analogy to understand the transport layer and the network layer, and how we can differentiate between what they do exactly. So let's say we have a household analogy. Hopefully this will make things a little bit more clear outside of that. So we have an analogy of we have a household that has 12 kids that are in Anna's house. And those 12 kids are sending letters to 12 kids in Bill house. In this analogy, the houses would represent the hosts. So these are the computers in the essence. The kids that are communicating with each other, these are the processes, and these apps are running on the host. The letters that are in the envelope or the app messages, these represents the message applications that are being sent. So the network layer, what is responsible for, it's responsible to deliver envelopes from one house to another. But the transport layer is responsible to make sure that the kid gets the right letter from the right sender. This is how the two layers work. So but the network layer will send will send the mail or the envelope to the specific house, but the transport layer say, hey, this is specific mail letter is intended for the specific kid, so it knows how to specifically supply it to that. So that is the idea and what we're going to discuss today, mostly the lecture that is being focused on. So to make a distinction between the two layers, we said that the network layer provides logical communication between the hosts. Think of it as getting like an envelope from Anna house to Bill's house. The transport layer would provide the logical communication between the processes inside the house, between a kid from Anna's house and a kid from Bill's house. We just want to make sure that the right kid in Anna's house talks to the right kid in Bill's house. So the transport layer relies on the network layer, but also handles it by handling delivery details. So we use the network layer for us as an initial step to send the envelope, but we rely on the transport layer to deliver the specific processes to the right user. So that's the idea. Together, these layers are the foundation, or when you think of a server and a client, this is what it's getting done. We are using the network layer based on the source IP and destination IP, And for the network layer, it uses the sockets with the processes to deliver and make sure that the specific process is going back is the output for the specific user. So to give an analogy outside of the household is that you're in your house and maybe you have siblings or your family is using you are both requesting HTTP request on Google Chrome, but you are requesting something, a web page that is different from your relative in the household. The transport layer makes sure that you are receiving the web page that you are requesting. The network layer is responsible of sending that request. So, well, mainly this chapter is about the transport layer, not the networking layer. So we want to see an example of the transport layer in action and how it works. So we will start with the sender first. And the sender obviously is usually us. We are responsible for preparing the application data so it can be delivered across the network. So the first thing that happened is the initial step is the application layer message. This could be anything that you are doing on your application. It could be an email, a web page request, or a video you are watching. What would happen that is the app hands this message down to the transport layer. So the transport layer would receive the message from the application. This is its input. The raw data needs to be prepared for transmission. Then what would happen is that the transport layer itself, we're still at the transport layer. So it determines what information needs to go into the header. This includes like stuff like the source, the destination, the port numbers, sequence numbers, and possibly some error checking codes. And these headers ensure that data can be delivered to the correct processes on the receiver side. We will have a detailed example of the segment header field values throughout this lecture, but that is what happened. So then the transport layer, what it does, we're still in the transport layer. It combines the header with the application message, and then it will create a segment. And this segment is a unit of data that the transport layer needs to send to the network layer. So we're in the application layer. The user is writing a message and it sends it down to the transport layer. The transport layer adds header values, and this is the idea of encapsulation, and it also creates a segment. So once the segment is created, the transport layer would go down and hand it to the network layer for the IP. Here, the network layer, we know it delivers host-to-host delivery. So it uses the IP address, but the transport layer ensures the right application on the receiver side will get this data. After that, we have it. After we are at the network layer, the data will get passed, obviously, with the link and physical, and then it will be sent to the other side. So this is the idea of the sender. For the receiver job here in the essence is that it has to take the incoming data that is being passed from the sender and deliver it to the correct application. So first thing is that the network layer what will do is that it will hands the segment up to the transport layer. Obviously, it goes all to the physical link and network, but when it gets to the network layer, it will hand it back to the transport layer. Then the transport layer would receive that message from the network layer. It would check the header fields. It will look at the destination port number to decide what this process is and who it belongs to. And this step is crucial. This is the step that we call demultiplexing, where we unwrap or in the essence unwrap the packet that is arrived, and then we send it to the right application or the right user. So after checking the header, the transport layer would remove the original application message, and this is at this point the raw data is ready to be delivered. And then finally, the transport layer would deliver the message back to the correct user, and by using the socket. This ensures the right application like your web browser is getting the data that is intended to do. So that is the big picture from a receiver and sender idea. The sender will take the application, wrap it into a segment, and passes it to the IP. The receiver would get that segment from the IP. It will check the header and extract the message and pass it to the correct process. So this is the end-to-end process, which makes the transport layer very crucial in the internet communication. Otherwise, we can use the network layer to deliver host to host, but that many details is going to be very important for us. So we have two main internet principal protocols, and these are going to get repeated through this course a lot. And it might be repetitive that you hear them more than one time. But TCP, you can think of it as the work of the house. It delivers all these features that we see here that is reliable in order delivery, congestion control, flow control, connection setup. And this is why that we have web browsing, emails, or file transfer. They depend on TCP because it is more ideal for them. And then we have UDP, obviously, it is unreliable in order delivery, and it's essentially a no-frills extension of IPs or best ever service. It is faster, but it is used in application where speed matters more than reliability. And that is mostly like gaming, online games, and voice calls. So importantly, neither the TCP or the UDP, we have to keep aware of that, is they provide certain services, but they don't guarantee things like delay or bandwidth. Meaning that delay, we can't promise low latency with these protocols, and the bandwidth, we can't promise a fixed throughput that is getting outputted back to the user. That's because the internet service provider or the IP itself, it does not provide these guarantees. So the transport layer protocol is built on top of the IP, so they inherit both its strength and limitation. So when we talk about latency or bandwidth or delays, this is more related to the physical aspect. And we covered a little bit of that in chapter 1 with where we have different transmission lines and backbone cables that provide us different intrinsic and extrinsic features for us when it comes to delivery. So going down on the roadmap, we have discussed the idea of the transport layer from the sender and receiver. And now we're going to talk about important principles, which is multiplexing and demultiplexing. And this is how the transport layer will manage the data. So to give you a general idea, multiplexing would, at the sender, would combine the data from the application and prepares it for transmission. Demultiplexing at the receiver, it separates the incoming data and delivers it to the correct applications. So let's see how the transport layer makes that happen. So this is what multiplexing and demultiplexing would look in practice. On the left, we have multiplexing, and on the right, we have demultiplexing. So on the left, specifically, we will talk first about multiplexing, is that we have multiple applications that are running at the same time. And these are just examples. It could be Netflix, Firefox, and Skype. What the multiplexing idea is that the transport layer would take all the outgoing data and combines it into a single stream that goes down the network. On the right-hand side is the multiplexing. This is mostly regarding the receiver. A single stream of data arrives at the transport layer, and its idea is to separate the data back out to deliver each piece to the right application. So this is how you can browse web, stream video, and make call at the same time without everything getting mixed up. So when you hear multiplexing, think of this is more of the sender, and we combine the data. Multiplexing is the receiver, and we are splitting all the data. So a lot of you guys use multiplexing in your day-to-day, right? You're doing several things. You're probably listening to music, and you're writing an email, or you're reading. I can't multitask.
Yeah, you can.
No, ever since when I was in school, And I see a lot of students in the library where they listen to music and can read. For me, I can read, but I cannot interpret what's going on.
You have to find the right music.
It's
That's what
probably
it is.
it's probably the right
My
music.
wife, she listens to classical music. She can't focus on nothing else.
So there's no
Me,
there's
I
no
listen
lyrics.
to, like, yeah,
Okay,
basically.
okay.
You just listen to the tones and it just,
Yeah.
you have to try.
Yeah, you have to try it. Yeah, when I sometimes go on YouTube, there's I think the lofi music, which is like live 24/7 that gets repeated,
Yeah,
and that kind of works. But you know, everyone has its
yeah.
has its own. Yeah, some I see that some students don't. They usually like they're doing something while working. So when they read, I had a student, a colleague, when I was doing my PhD, he would use the squash ball,
Okay.
you know, one of those stress balls, and that would help him like I don't know, it will help him like stay relaxed. And when it comes to memory, he says that it helps me with memory, like remembering the what have been said, or in the essence, like to make sure that the idea, yeah, some students is just different from one another. Okay, so let us continue. So again, at the client side, multiplexing is we are supposing that your laptop is running multiple applications. Maybe you're streaming a movie, Netflix, and it's on a smaller screen. They're using Chrome to load on the web page, and you're using Skype to make a call. Obviously, you're not doing all of those at the same time, but this is the example that we have here. So each application will generate its own application layer message. The transport layer, what it does is on the client. It takes all these going messages and multiplexes them, or condense them into one segment. Then it attaches the correct source port number, so the server knows which app data it belongs to, and all those segments are sent down to the network layer as one combined stream. Multiplexing is when they receive it at the server. Those segments arrive at the server. They come in or as together, part of the same flow. The transport layer would look at the destination port in each segment, and then it demultiplexes the data to the right user. So it will see that, hey, we have port numbers, and this is the idea of port numbers. Not only they are assigned for specific processes, but we can use them for maybe classification or to distinguish between them. So we know that port number 80 is usually for HTTP, and 443 is for HTTPS, and this is regarding Chrome request. And then we have a port number that is set for streaming, or that would specify to Netflix, and maybe for voice over the internet or voice over IP is using Skype. So in the server, it can receive multiple application and still keep each client data separated. So here's a scenario that we will do is that on the client side, you might run here's what's going on. Here we have two different clients. I want to show you the idea when we have multiple clients, how it would work. So on the client side, you might be running Skype, Netflix, and Firefox. And we said that each of those apps generates its own data. And then the multiplexing comes and combines all these messages into one. And then these requests are being sent to the HTTP server, which is running on the Apache web server. And at the server, the transport layer, it will reverse demultiplexes the incoming data and passes it to the right request for the Apache to process it. While we have another client who can make other requests, and the transport layer would ensure that the traffic coming from two different clients is going in the right process, in the right order, and that goes back to if we are using TCP or UDP. So now let us just focus on one application, which is the browser, Firefox. Here we have. So Firefox, when we are using Firefox or HTTP, we are using whether we are making a request or whatever we are doing on HTTP, we are generating an HTTP message in the essence, and we are using port 80. So the message is given to the transport layer on the client, which wraps it into a segment with the correct port number, and then the segment travels across the internet and reaches the server transport layer. So then the server would look at the destination port and say, hey, it is for Apache, and delivers the message there. This shows how the transport layer ensures the client app, Firefox, connects to their server app, which is Apache. Now, considering that we have two clients on the same server at the same time, because we are working in real time. When it comes to real time, we might have multiple users within a local area of network or a wide area, but there's real time clients that are potentially doing the same thing. So the server transport layer receives the segments from both clients, and it wants to know, hey, which request is coming from which client? Is it coming from client one or client two? And how does it distinguish with that? It uses the sock pair. So it uses the source IP plus the source port and the destination IP and destination ports. So this unique combination is going to help it separate that client one is using Firefox and client two is also using Firefox with a different session. So they're completely isolated from each other, but the request is kind of the same. They're both using Firefox. So remember that the source IP and destination port plus the destination IP and destination port is what helps the server or the receiver distinguish between the requests that are oncoming. So to give you a little bit of idea of multiplexing and demultiplexing, I hope the idea is very clear now, but we will take it outside a little bit from the network and infrastructure and talk about and give a little bit of analogies. So the first thing is when we have cars, and this is the idea of multiplexing. We have cars from different ramps that are entering all in the same highway. So this is multiplexing where it combines many separate flows into one shared road. And this could be like multiple applications sharing the same transport channel. The highway signs is, you can think of it as demultiplexing. So when you're at the right exit, you're gonna exit. So it splits into multiple exits and each car chooses the right exit for it depending on its destination. So just like the transport layer, it has these segments and it knows to deliver to the correct application. A little bit about the airport, airboarding signs itself, it's multiplexing. So you have different tickets classes, can be economy, sky priority. What is sky priority? Does anyone? I have never heard of that. Yeah. And basically the same idea would be repeated here is that it would multiplexes many groups into one transport system. I think it has to do something with maybe, I don't even know, Air France, maybe something with
Yeah, probably with the airlines itself.
Yeah, with the airline itself. When it comes to TCA, pre-check versus main checkpoint is demultiplexing. So people again are separated on which line they choose. So that is where the transport layer would look at the header info, like the port number, and to route each segment to the right place. And finally, that's what it is.
It's basically like when you go through the TSA,
Mhm.
the fast check-in. That's
Yeah.
basically what it is.
That's what it is. Yeah. Yeah. One time when I was traveling, I entered the wrong side of these. One of the wrong side, and I was waiting in line, but it was a very short line compared to the normal one. But then when I got to the end, you're in the wrong line. Got to go all the way back. So, so you got to be careful with these. TSA pre is obviously you are pre-checked
They
in.
have all the credentials and everything.
Right.
They don't really have to do that full search like
Yeah,
regular people.
exactly. Yeah, you never know. So, I mean, it's probably better to do it, right?
It's better to do it, but if you only travel like that, if you don't really travel like that, it's pointless to be honest. I have a best friend, she does it all the time, but she travels for work.
Right.
Yeah, exactly.
It's $70 for a whole.
Yeah, it's like cheap. It's
For 4
cheap.
years. Oh yeah, it's really.
cheap. But I mean, the convenience.
How do they verify your info maybe haven't changed?
Your ID, passport, just regular documents to verify that it's you. Like you lived in your state for a particular amount of years.
Okay.
Yeah.
Cool. And yeah, so lastly, we have the boarding gates is an idea of demultiplexing is that passengers are separated into boarding lanes, and this is making sure that the flow is intended to the right endpoint, the correct process or the application. So more of scenarios, and this time we are showing both the processes that we have and the sockets. So the processes are highlighted as P1, P2, P3, and P4, and the sockets are highlighted in yellow. And we want to see which are the entry exit points for data. So in this example, P1 would communicate with P3 and P2 would communicate with P4. So now let's focus on the multiplexing at the sender, which is the left host.
With P1 and P2, the application for P1 and P2, it's distributing to P3 and P4 for the simple fact that it has two sockets in there.
Yes, so you have to have
So it
one,
can only do when it has enough sockets.
but we can have multiple processes on a certain side. So that left side, we can have P1, P3, P4, all the way to P10. Each one will have its own socket, and it will have its own, obviously the host IP would be the same, but the socket is gonna change. We're gonna see that in just a little bit.
Okay.
So on the sending side, processes P1 and P2 would send their own data to the sockets. So the transport layer takes these separate data streams and multiplexes them. That means like putting the data into segments and adding a transport header, which is needed for demultiplexing later. At the receiver, the receiving side, which with also using the transport layer, it performs the opposite operation. It uses the header information inside each segment, such as the port number and the host IP that is coming from, and it ensures that, hey, data from P1 is delivered to P3 and from P2 is delivered to P4. So that is where we have multiple processes and multiple sockets. Next, we will look at how, if we are using a different protocol like TCP or UDP. So this is again how it works, multiplexing. It receives the IP datagram. It contains the source IP address from the sender, and it contains the destination IP address that the host is receiving. This is the starting point to figure out where the segment should go. And for the datagram, it carries the transport segment, and each segment contains one transport layer segment. Inside that segment, there is a header plus the application data. So the application data here is the payload, and the source port is the port number for this specific process. The destination port is also the destination port for the receiver. So two fields are important here that we have to keep track of: the source port number and the destination port number. And they're crucial to tell, hey, which process or sockets should be delivered to the right one. And yeah, that is here just showing you. So first, we're going to start with connectionless demultiplexing, which is UDP. And if we can recall a little bit about chapter 2, specifically the programming assignment, when creating a socket, the application or the programmer himself specifies a local port number, which we can see here as listed as 12534. Now, when creating the datagram to send to the socket, you must also specify the destination IP address and the port number. That is important. And then the receiving side, when a host receives a UDP segment, it checks the port number and directs the segment into the right socket bound to that port. But here, most importantly, is that if we have multiple clients that send datagrams to the same destination port number, even with different source IPs, do they all get directed to the same socket at the receiving host? And the idea is that because the UDP demultiplexing is based only on the destination port number, it does not use the source IP or port number. That's why we said it's not reliable in that sense. So now let's look at an example of demultiplexing with UDP. So we usually have 3 hosts as usual, right? And on the left-hand side, we have process 3, which is known as P3. And we create a datagram for it with a specific port number, a local port number, and that is identified as 9157. On the right-hand side, we have another client, which is, we can say P4. And we also create a datagram for it, and we give it a specific port number or local port number, which is 5775. In the middle, we got P1, and which has a datagram that is associated with a port number 6428. So now P1 and P3 will communicate with each other, and P1 and P4 will communicate with each other. Why does P1 communicate with both processes? Because here it's the server, it's the one that we ping for our request. So in the first example, we see datagrams that are being exchanged from P1 to P3. So let's look at what P1 is sending to P3. First thing is that we focus on the source port number, and that is the same port number, the same local port number that it has. And the destination port number, which is 6428, that is the associated port number with process one, or the server and known. And we said that with the programming assignment, the server must have a static port number such that we can ping it. So we will see that when P4 pings P1, it will use the same port number that we use from P3 to P1. So now what would happen is that P1 would reply back to P3, and as we said, and we know in chapter 2, we'll use the destination port number, and that is 9157. Let me just show you. So we'll use the destination port number, and yeah, it just flips the processes. So it's just like the idea of when you mail something to another address, you attach your address as the sender and the receiver address, and then he receives it, and then he sends.
You want to see? Okay.
Yeah.
Okay, that's good.
Okay. So on the right-hand side that we have, the same idea would get repeated here, and this is just for us to try out. We want to know what will go in these blank spots. So obviously it's going to be the same thing. When P4 contacts P1, it would use its own source port, which is 5775. And then it would also use the destination port, which is 6428. When P1 sends it back to P4, it would use its own source port, and it would use the destination port of P4. So here with UDP, we do not provide, we don't specify the destination and source port number. And this is just for you to figure out for yourself. So this is how multiplexing and demultiplexing works in UDP. Now, when it comes to TCP, it is identified by multiple things. It not only uses the port number, but we are here using the IP address, and it uses a 4-tuple. So it is a little bit more complicated when we compare it to UDP, because we saw demultiplexing was really simple, and multiplexing is really simple in the UDP. Because TCP is like connection oriented, that means we have a sending and receiving side, and we want to identify the sender and the receiver. So the 4-tuple that we have is we have the source IP address with the port number and destination IP address with its port number. So the first thing that obviously demux is a short acronym for demultiplexing, and it would use all the 4 values that are found in the tuple to deliver the segment to the correct sockets. And it's more stricter because UDP just relies on the destination port. It does not use the IP address. So to sum up TCP, how it works is that the server can support many TCP sockets, and each socket is uniquely identified by the 4-tuple and corresponds to a different connecting client. So let's look at the demultiplexing with TCP. And we have the familiar 3-host setups. In the center, we have the Apache, the HTTP. This is basically host B. Exchanges messages over TCP. So we have host A on the left, and we have host C that is on the right. And the IP addresses here obviously would be replaced with the specific IP address, but here host IP host A would use the address A, and host C would have a specific IP address as well. So we want to focus on the communication that would happen here. So the first thing is first, obviously, P1 and P4 are communicating with each other. And P1 is the host, and we want to have the specific process for the Apache server. So for the datagram that is being flown from A to B, which is P1 to P4, the source IP is obviously going to be A here, and the source port number is going to be 9157. That is the local port that is being used that is being used by P1, and for the destination of IP B, which is the Apache server, the destination port would be obviously 80 because we are using HTTP. And then the reply from B to A, from the server back to the client, it uses the address, which is B, and it also uses its own local port number, which is 80. And the destination IP is A, that's the receiver, and its own port number, which is 9157. On the right-hand side, we can see also datagrams that are flowing from host C to the Apache server as well, especially going from process P2 all the way up to P6. And then we can also have another process that goes from P3 to P5. That means this specific client or host, the host on the left is only has one client or has only one process. But here the client on the right-hand side has several processes. You could be watching Netflix and working as well. We want to notice one thing, notice all the three datagrams arriving at the HTTP server have the destination port of 80. So regardless of which processes that is on there, it's using the same port number that is 80. So now with UDP, it would only use the destination port, but TCP, since it's connection oriented, with multiplexing, it would use the 4 tuple. So each one of those messages, the 3 messages that we have, has a unique 4 tuple, so they're correctly mapped to the right processes. Does anyone have any questions about this? It's understandable? Yeah? Okay, good. So just know that with UDP, we are not using the IP address, but TCP, we're using the IP address and the port number as well. So as a summary, and a recap, is that multiplexing sender combines data from multiple applications and transports them to the transport layer. Demultiplexing is the receiver who uses the header info to deliver each segment to the correct process. UDP is simple, faster, connectionless, and when it comes to the multiplexing, we use only the destination ports. TCP is more connection oriented. It uses the 4 tuple and allows many client connections that could happen. So these are the mechanisms that are being used to enable many apps and many clients to share the internet without confusion being done. So that is the wrap of multiplexing and demultiplexing. In the next lecture, we'll recap those as well, and we will move on to the new topic of the roadmap of the transport layer. Okay, so what I wanted to do is, we have some time. We can talk about programming assignment a little bit here. Okay, so for 20 and the end of it. So for the programming assignment, you will implement a client and a server, obviously, and your client is going to run on Eustace, and your server is going to run on Eustace 3 to communicate with each other. So you should already by now know how to log into Eustace using your SSH with your NID and your password. And obviously, if you're outside the UCF Wi-Fi, you have to use the VPN. Here's some guides that you have for yourself. But what we want to get into is that the assignment is due on the 5th. Obviously, you always have the 2 days after the due date, but you have to keep in mind that there is a late fee penalty that would get applied. So in what I showed in the demo is that we input a lowercase letter and we are getting a higher the response in uppercase. For your programming assignment, you will do a client and a server. For the client, you will input arithmetic as an input, and these are going to be numbers, could be addition, division, and the server is supposed to acknowledge these requests and reply back to you. So it is ideally the same idea that we have. But you have to make sure that the receiver is receiving the right information and outputting the right information, obviously, for you. So it should be relatively similar to what we have done. It's just that the motive is different here. So for what to turn in, you have to turn in a report similar to the lab or the homework. This is basically a brief step-by-step of how you set up both servers and you running the application or the programming code that you have written. And then you also have to turn in your client code and your server code for the TAs to run. So you can use any programming language. It does not really matter what you use. If you're using C to program when it comes to running your code on Eustace, you will use the GCC, and this is the command for you to run. So also for your port number, choose something that is greater than 1024 to be safe, and choose a server port number above 5,000. These are just like recommended. And what could happen, as we also seen in the last lab, is that when you have a specific port number and you exit out the connection, it doesn't exit out the port number right away. There is an idle time that you have to wait for. So you probably have to just change the port number or just wait a minute for it to process again. So just keep that in mind. And if you have any questions regarding that,
Service that you're reading all numbers.
yeah, the numbers here, I mean, try to input the same numbers to get the same result.
Okay.
But we want to see that, hey, you're inputting multiple numbers and multiple arithmetic, like division, okay? For the homework, just to quickly cover, I have some questions about it. I figure I share these with you as well. First, for question 2, you have to answer the GET request for both websites. It's not like the lab where you have to choose one of the websites. So both have to be done. And oh yes, with that, I already mentioned in the last lecture that you will get a redirection. So you have to trace or telnet into the correct path, the newer path of this website. And yeah, that is it. We don't have anything else. I will see you on Monday where we pick up on the transport layer. Okay, let me stop sharing. Okay. Yeah. Have a good one. Just